A uniform resistance wire AB has length 50, diameter 0.36. Okay. The resistivity of the metal is given. So this is rho resistivity, length L and diameter D. We can assume that if they didn't say otherwise, that your wire would be a cylinder shape. So you're going to have some cross-section area. You're going to have some length. And of course, you are made of some material, so you have a resistivity. We need to show that the resistance wire is 2.5. Okay, so this one, you just need to follow the equation R equals to rho L over A to find resistance of any conductor based on its dimension and material. So rho will be 5.1 times 10 negative 7. L must change to 0.5 meters. Keep everything in SI unit because it's ohm meter, so best to use meter. So this will be 0.50 divided by area. Oh yo, area. They give us diameter. So area, generally we can use pi d square over 4, which is a variation of pi r square, but it's easier to do, just do pi d square over 4. So actually we can change this to rho L pi d square over 4. Or we can put the 4 on top, 4 rho L over pi d square. So I'm just going to put the 4 on top because, actually, let's put the 4 at the bottom. Okay, so this one is pi times, where's our diameter? 0. Oh, yeah. This is in millimeter. We need to convert. Okay. Okay, maybe put the 4 on top. So this will be pi. Okay, diameter must convert very carefully. 0.36 milli. And the milli must be inside the square also. So 2 times of the milli. This should be correct. Alright, calculator. Should give me, what's this calculator? Oh, 2.50. I guess no need so many. 2.51 is okay. So we got 2.505 actually, which is roughly to 2.5 ohm, which is what they want us to prove. So it's nice when they give the answer. So first mark comes from you using the equation for resistivity or resistance, R equals rho L over A, either written explicitly or in the form. Best to write it explicitly. And secondly is for your calculation, substituting all the correct values and getting your final answer. 2 marks. Alright, let's go to the next part. This is where it gets a little bit strange because you now are putting the wires AB in a circuit. So the wire AB was this one, right? Yeah. Resistance was 2.5. So this wire is connected in series power supply with a resistor. EMF is 6 volts and its internal resistance is negligible. Oh, thankfully. The resistance of R, 2.5, and another uniform wire is connected across. CD is 100. Diameter 0.18, same metal as AB. Whoa. Let's write down some facts. So this wire is 50 cm, 2.5 ohm. So I'm going to write here 50 cm, length of AB, and resistance of AB is 2.5 ohm. We need to calculate the current supplied by E. To find current supplied by E, that's current through the battery. Okay, so here's what we can use. We'll go with our V equals to IR ratio, but we need to modify a bit. So this will be the EMF supplied, or rather the total, since there's no lost volts, equals to I times the R total. So that would be current. What's the EMF? Oh, 6 volts. Why they write here and not up here? 6.0 volts. Okay, this will give us 6. What do we put in that current? We don't know. We are trying to find that. So I, R total. Okay, we need to combine this 2.5 ohm in series with this one. So R total, and then we need to combine in parallel with the one down here. But what is this resistance? How do we find the resistance? They didn't really give us information of resistance. But they did give some. They said the length is 2 times. Diameter is this. So if we scroll back or we think back to our earlier R equals to rho L over A, we can actually do a ratio. For this new wire, what is constant? They're made of same metal, so rho it didn't change. The length, become longer lah. Diameter 0.18. That's 0.36. The diameter did change. So we can't say much more other than 4 rho L over pi d squared. The only constants here are 4 and rho and pi. So I guess we could do a calculation or we could do a ratio. I think I'm going to go with a ratio. R is proportional to L over D squared. This is the old R, which is 2.5 ohms. Not old R, RAB. RAB. So this new RCD, let's sub in the values. How many more times is it? Let's put here L over D squared. So this new wire has 2 times the length. 2. Because you are going from 50 cm to 100 cm. So 2 times. I'm going to write some notes here, I guess. Where to write? I also don't know. This one is 2 times of LAB. So I put a 2 there. Okay. Is all AB. How about the diameter? This diameter, the original diameter of AB was 0.36. Oh, it becomes smaller. 0.36. Okay, what's that ratio? So this 0.18 is smaller. Okay, so this is how many times? Let me divide 0.36, 0.018. 2 times smaller. Yeah. So half of the diameter of the first wire. So we're going to put a half here. So if I want to take out all these green color values, which is the multiplier, the ratios, that would give me 2 over 1 over 4, which is really is 8. Okay. So this will be 8 times of the original. And this is the new wires resistor. So this is one method that I like to use. You can use definitely other ratio methods, other calculation methods, but this is one of the faster ones lah. Okay, so it's 8 times of this old wire. So 8 times Okay, so I'm right here. This resistance is 8 times of 2.5, which will be 20 ohms. So the total resistance, okay. We need to combine in series, in parallel. Oh, wait, this one and this one is 2.5 in parallel with the 20 ohm. Treat them as resistors. So I'm going to combine them in parallel. So 1 over 20 plus 1 over these two in series, we can just add. So I'm going to put 2.5 plus 2.5. Negative 1. Current, we should get 1.5 amps. Alright. It was tricky. 4 marks for this. The first mark comes from you knowing what is the new resistance of this wire. Either getting 20 ohms, multiplying by 8, doing some kind of ratio, or just showing that you know it's 8. That's 1. Then you find the circuit resistance of 4 ohms. So some people prefer to do this separately. They may do this. This one will give you 1 mark. Then if you VIR and you use this thing to calculate the final answer, that is A1, the final mark. I did everything in one step, so that's all in one lah. Alright, so this one, I should write side notes. R total here would be 4.0 ohm. So we can write 1.5 as our current, final current. Okay, next part. Find the power transformed in wire AB. Power has quite a few. P equals to IV, P equals to I squared R, P equals to V squared over R. Which one do we want to use? It's so many leh. The idea is you want to use what information you know. So wire AB. What do you know about wire AB? Do you know current? Not exactly. Do we know voltage? Not exactly, but we could find some here with the help of a potential divider. This is going to be tricky, man. But we definitely know R. So we're going to choose an equation that has R in it. So depending on how comfortable you feel using potential dividers or finding current, you can choose either way. Alright, I think I'm going to go with potential divider. So this 6 volts provided will be shared across each parallel line. So the first line is 2.5 ohm, which means the resistor here will take some share. This resistor or the wire here will also take some share. They all take share, ma. They all want a little bit, okay? So how do you find that ratio? We gotta do... let's ratio. What shall we ratio? What do you want to find? VAB, right? So we'll take VAB ratio over... I think we also over the total, which is 6 volts provided to both in series, over the ratio of the resistance. So that will be 2.5 over the total resistance. So 2.5 plus 2.5. Okay, so we should get a VAB of 3 volts. Okay, so we got 3 volts here. Means this guy said, I take 3, The other fella said, oh, I take 3, Hey, actually, we didn't need to calculate. They have same resistance, they will take equal share. So 6 divided by 2, you take half, I take half. 3. Aiyo. Okay, this is definitely easier than finding current. So we're gonna go with this. I don't need to calculate lah. So 3 volts for AB. And what's the resistance again? 2.5. Alright, so we're gonna write there 2.5. That should give us 3 divided by 2.5. 3.6 watts of power. The first mark is whatever equation you use. Second mark is if you get the final answer. Okay, so you can write 3.6. Part 3. The finale of this question. Is it the finale? Yes, it is. Oh, this is where it's a bit tricky. The potential difference between the midpoint of wire AB and midpoint N of CD. We need to find that. Wait, what? We need to find the potential difference between midpoint to midpoint. Okay, this one, we're going to go all the way back to the circuit and just stay on that picture. Potential difference. I'm going to rub off some of these things now because we will need the space. Oh, we will need the space. So, potential in potential difference are actually 2 different things, in case you didn't realize. What was this one again? 20 ohms. I forgot. Oh no, what's the thing? I dropped it off. Didn't realize. I think it was 20. Yeah, it's 20. Alright. So when we say we want to find the potential difference between the midpoints, 2.5, it's like saying I'm going to connect a voltmeter between here and here and I measure it. How on earth are we going to find that value? You need to know what does potential drop mean. So in a circuit, remember, we looked at in an earlier theory video, as long as you don't spend the energy, you are at a potential of 6. The moment you spend some energy, you drop potential. In the first wire, we already calculated, let me rub this off, that your potential drop or potential difference was 3 volts. Drop. And then it will drop another 3 volts here. Drop. Then go back to battery. Okay, then 0 already, no? Tick, 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 tick. Okay, get the idea? You go in a circuit, you lose energy, ma. Drop, drop, drop. So in this point B, from 6 volts potential, okay, this is potential, 3 volts potential difference, means a change. What will be your potential at B? 3 volts. 6 minus 3, 3. You drop. You are at 3 now. Then later here, 3 minus 3 go to 0. Okay, very good. Potential difference drop, I should mention. So we do the same thing for the other line. From the other line, 6 drop all the way to 0 eventually. So this will be, we know this part is going to be 0 potential at D. 0, 0, 0, 0 all the way home. In between, can we say that this will be from 6 to 3? Can we say that? Actually can. Because in a wire, the resistance is rho L over A, right? But if we just look at wire CD alone, what is changing is the length. Maybe we say, we look at this section, what's the resistance? If we look at the full length, what's the resistance? It's a ratio. So in this case of looking at the single wire, R is proportional to length. The longer you are, the more resistance you have. So if your full length is 20, if your full length gives 20 ohm, means your half length is just half of that. So that will be 10 ohms here, 10 ohms here. Total 20. So the potential drop across a 10 ohm and 10 ohm, you share lah, okay? 6, each one take 3. So the first one take 3 volts, the second segment take 3 volts, and it's a potential drop. Potential difference, PD. So 6 minus 3, that will give us a potential of 3. Now we are ready to find the answer. Almost. One thing is still missing. We know the potential at N. We don't know the potential at M yet. Okay, so we need to apply the same idea. 2.5, 6 minus 3. Okay, so if we were to split up the segments, equal length, midpoint, right? So that means here you will drop by, what is half of 3? 1.5. Drop. Then you drop again. 1.5. Drop. Potential difference is difference. So 6 minus 1.5. What's the value? It's 4.5. So at this point, we are at 4.5 at point M. Now we can find the answer. What is the difference between 4.5 and 3? That will be your answer. So let's go and write this out down there. 4.5 minus 3. So these 2 marks, so maybe you should try to explain a little bit. PD drop from A to M. This one is 1.5. PD drop from C to N is 3 volts. So we're going to compare that. So we say potential drop or potential difference from A to M, half of the length, is 1.5 volts. Potential drop from C to the N midpoint is 3 volts. Hence, potential difference, what's the potential difference? M to N is 3 minus 1.5. 3 minus 1.5, this will give us 1.5 volts. And that is our answer. So this one is A1, first one, M1. This is just restating what we just looked at just now. So I'm going to go screenshot and do one final recap. I know this is a very strange idea when you're trying to think about it. Let's look at it one last time. So this circuit, okay, recap. You are the high potential, 6, 6, 6, 6, 6, 6, 6 all the way. Like I could just say, oh man, you have lots of energy here. All 6. Once you spend some energy by going through resistance, your potential decrease and there's a drop. And when you want to find the difference between here and here, you just need to subtract the potential, 4.5 minus 3. If this is strange to you, you imagine this. You are standing on a very high bridge, very high up in the sky, and you tie 2 ropes. One rope goes down by 1.5 meters. I would say 1.5 meters rope. Okay, you are very high up here. You are 6 meters high in the air. This is the ground. The other rope goes down by 3 meters. Much more. Oh, then my scale is off already. 1.5 is this short thing. 3 meters is woo. And you hang a coconut on the end. This one is 3 meters. Then I ask you, okay, What is the height difference between the two coconuts? If I tie a coconut up there and I tie a coconut down there. What is the height difference? What would you do? You just take 3 minus 1.5. Oh. That's the same idea what we're doing here, except that we're doing potential. From very high, you drop down. From very high, you drop down. What's the height difference? It depends on how much you drop. Okay? So keep that analogy in mind. High to low, potential and potential difference are different things. But I think that's pretty much it for this video. Hope that was helpful in doing this tricky question. I'll see you in the next one.